All right, good day, everyone. My name is Riley Edwards, and I'd like to welcome you to the virtual William W. Hay Railroad Engineering Seminar today. Before I introduce our speaker, I'd like to ask our listeners and our participants to submit your questions using the Q&A box at the bottom of the screen. You can also upvote your questions by hitting the thumbs up symbol, which will add greater priority to them as we address them at the end of the seminar. I'll help to moderate the questions at the end of our seminar, and they'll be fed to our speaker for responses. The William W. Hay Railroad Engineering Seminar Series is sponsored by the Rail Transportation and Engineering Center here at the University of Illinois at Urbana-Champaign. On behalf of all of us, we thank the Association of American Railroads, BNSF, CN, Hanson Professional Services, and Union Pacific for their support. It's greatly appreciated by those of us in rail tech, and I know by all of you that are participating today remotely. I'd also like to extend a welcome to our more than 220 participants from 21 countries on 6 continents who have registered for today's seminar. This list includes representatives from freight and passenger railroads, transit organizations, federal and state DOTs, engineering firms, universities, and research organizations. We're very pleased you can join us, and we know that we're going to have a great presentation today. We'll also issue PDHs for those of you that have completed the payment online. If you need a link to the payment process, send us an email at the address of hayseminar@illinois.edu. As we begin our fall semester, we're going to be announcing additional Hay seminars soon. I will describe the details on our next seminar at the end of today's. So now I'd like to introduce the topic for today's seminar. Railroad track design methods must provide guidance for assessing the trade-offs between ballast thickness, subgrade properties, and traffic. The methodology for developing a design considering these to protect the subgrade from ballast pockets and other forms of distress will be discussed as a part of today's seminar. Our seminar today will also highlight the methodology and provide insight into its application for assessing change related to the operating environment and maintenance activities. These methods used to assess some of the questions related to how changes affect economics were developed by our speaker in his work with Professor Ernie Selig at UMass. And it's exciting that our speaker today continues the legacy of Dr. Selig. From assessing the impact of stiff roadbed and assessing maintenance scenarios and operating changes, the techniques that we'll discuss today provide a means to determine the design life of track and also indicate how we can assess each particular design scenario we may be encountered with. Practically, these techniques require substantial data on roadbed condition, performance, and engineering properties. And there's a challenge in obtaining these necessary data, but once we achieve and overcome the challenge, we'll be able to use them for a variety of design and performance assessment applications. And this is what our speaker will be discussing today. I am honored to introduce my industry colleague and my friend, Dr. Ted Sussmann, our speaker today. Dr. Sussmann is an associate professor at the University of Hartford, where he teaches civil engineering and transportation-related courses. He's graduate program director, and he's helped formulate a curriculum in construction management. Dr. Sussmann's research is focused on geotechnical infrastructure engineering and railroad track design. He's co-chair of the Transportation Research Board Committee on Railway Infrastructure Design and Maintenance. Early in his career, Dr. Sussmann worked on the formation of a rail infrastructure asset management company. He has a PhD in civil engineering from UMass Amherst, where he calibrated piezoelectric sensors for highway vehicle way and motion use, stabilization techniques for railroad subgrade, and measuring and modeling track load deflection behavior. He's also worked on GPR topics, ground penetrating radar, high-speed rail track design, and a variety of other areas. Dr. Sussmann is also a part-time civil engineer at the Volpe Center and is co-author of the book Railway Geotechnics. So now I'd like to turn it over to Dr. Sussmann, who will present his seminar titled Ballast Thickness Design for Changing Environments. So welcome.
Now that I unmute, I just got a call from a phone number that wanted to know if I wanted to extend my warranty on my car. So right at 103 without fail. Thank you, Riley. I appreciate that. Great introduction. And I'm happy to be here. When Riley first asked me to give a lecture on track design at the stirred up a number of memories because it's not something I had been an area I've worked in recently in my current work, but it's an area near and dear to my heart. And this activity of putting together this presentation made me pull out a lot of presentations from previous work that really brought back a lot of memories. So appreciate the invitation. I'm glad to be here. It's an honor to give this lecture. I want to start out by saying to the students and the young engineers in the audience, stick with the rail industry. It's great and rewarding career, and it needs you. So stick with it. Not always easy, but always rewarding. And I also want to say that this topic of ballast thickness design isn't just to determine the required ballast thickness, but it's a methodology to assess trade-offs between the applied load in terms of wheel load and number of cycles, the track characteristics, including ballast condition and thickness, subgrade characteristics, and design life. And one of the outputs of that methodology can be ballast thickness, knowing the other components. But if you know the ballast thickness and you're inquisitive about the design life under different operating conditions or different scenarios, it certainly is suitable for answering those questions. And that's where we'll spend a little bit of time today. And I want to just say that I'm going to dedicate this talk to Vin Terrell, who was a friend, passed away in the last year. He was a VP of engineering for Boston and Maine Railroad, and a lot of the thoughts that developed on the application of this design method came on the mornings after Vin Terrell came out to visit Dr. Selig while I was doing my PhD at UMass. And inevitably in the morning, Dr. Selig, Ernie, as we grew to call him as time went on, would ask me to come in his office and see if I could create a spreadsheet that could switch things around in the design method and solve a particular question. And that happened on more than one occasion and had some fairly good implications. So again, dedication to Vin Terrell, a close friend and past president of ARIMA. All right, I'm going to start out with a quote from Professor Hay, namesake of the lecture, and a quote directly from his book. It's common corrective for poor track has been to lay new and heavier rail. The money might often be better spent in increasing the strength and stiffness of the rail support. One might as well try to stabilize a sinking building by adding another story to it. William W. Hay, 1982. It's a great quote, and I think it illustrates the issue that the track and the substructure is really a system. And there's really two big ideas that this quote pulls in. One, track is a structure, and a lot of times in the heat of the moment, we lose the sense of this is really a delicate balance we have, balancing the ability of the rails to guide trains and the ability of the substructure to support the track. And another big idea in this quote is that really the rail serves as the transmitter of applied train loads to the track structure itself. And in the quote part where it says one might as well try to stabilize a sinking building by adding another story, adding a heavier rail to solve a substructure problem is simply adding more to the ability to get load in, not the ability to withstand those loads. In the paper Quest for an Ideal, there's a discussion of what is ideal track. This is a 1930 paper by Paul Chipman, given at the Engineers Club of Philadelphia. And in the paper, Paul describes an ideal roadbed. And his description starts out disregarding for the present the matter of initial cost, which is a big matter. I'll return to the quote. Let us briefly consider the requirements of a roadbed that is ideal. First, the load must be distributed over a large area of the subgrade. Second, the rail must have continuous support. And third, economical means for adjusting the surface must be provided. And, second bullet, the rail must have continuous support. I think that, if you go back to the 1930s and sort of transport yourself there for a minute and think about how track maintenance was done without the mechanized surfacing gangs we have now, I think bullets 2 and 3 become sort of easy to explain. Not necessarily the continuous support that's shown in the figure here, but the ability to support the rail without having ties that settle or shed their load. And economical means for adjusting the surface must be provided. This is pretty difficult in this type of track that Mr. Chipman is showing in the picture, because any sort of fixed track is hard to adjust. But with the maintenance equipment that we have, surfacing is readily available. Mr. Chipman goes on later in the paper and asks the question, what is an ideal roadbed worth to the railroad? What is an ideal roadbed worth to the railroad? And he goes on to say that a railroad cannot place really a value on an ideal roadbed, because an ideal roadbed would reduce the stress in the rail, limit rail breaks, improve ride quality, reduce deterioration, improve fuel efficiency, and it's a long list of items in that, which makes it very worthwhile. So, you know, in my previous quote, there are going to be people that say, yeah, there's always that spot where there's no solution to it. You got bad support and you need a heavy rail. And remember where we did it over in whatever area. And, you know, if we combine that thought with what Mr. Chipman's idea is here, is that, you know, using the most expensive component of the track structure, the rail, to correct a problem with the least expensive component of the track structure, perhaps, and that's the ballast. You know, I'll just have to use a quote from that great football coach, Bill Belichick. What are we doing, right? We should be using the least expensive component as readily as possible to fix problems with track support. So for an outline, to get into the bulk of the presentation, we're going to talk about the track design concept and philosophy, risks affecting the track structure, the changing environments that I allude to in the title, opportunities to apply that design philosophy, and give a summary. So getting into the track design concept and philosophy. So the track design concept is based on the track cross-section, ballast, subballast, and subgrade, where we design the ballast and subballast combined thickness for adequate load resistance, providing a profile for drainage in order to protect the subgrade from deformation and saturation. In order to do that, we have to ensure proper load distribution. The distribution of load from the rail to the ties is important. Getting adequate distribution from the tie directly below the load to the adjacent ties, so they work as a group. Load distribution along the track and along the ties is affected by the track support. Poor track support sheds load. Good track support concentrates load or distributes it properly. Soft track support increases rail deflection and engages a larger group of ties. Stiff track support tends to concentrate it on a central loaded tie, increasing certain stresses. Talking a little bit about how those stresses get distributed. The load distribution of the track is shown in these figures here, where we compare wood and concrete ties to each other in this figure to show how the load is distributed. And how the load is distributed, depending on track conditions and model parameters and the such, can vary greatly. But in this comparison with a track that has an 18-inch thick ballast, 60 KSI ballast modulus, and a relatively stiff subgrade at 8 KSI, the load on the central tie is reduced with a concrete tie, and the pressure is almost the same on the subgrade. So we can look at the bulb on the bottom. We can see that 10 PSI stress contour applying the subgrade that, you know, regardless of the surface interactions near the ballast and at the rail tie interface, the load gets distributed down through the ballast into the subgrade at nearly the same level. The track design philosophy basically is to develop a track cross-section of ballast, subballast, and subgrade to distribute applied loads to the subgrade at an acceptable level, protect the layer below, and provide resilient support to the tie. Protecting the layer below means that the ballast should reduce the stress in the ballast to an acceptable level for the subballast. The subballast reduces the stress to an acceptable level for the subgrade while maintaining their position and not intermixing, pumping, or otherwise deforming. That last component is known as limiting plastic deformation and settlement. The two ballast design criteria we're going to talk about in the design method today is excessive plastic strain at the subgrade surface, that's the subgrade squeeze in the top figure, and excessive plastic deformation, ballast pockets in the bottom figure. These two subgrade failure modes were the two most common and became a topic for me as an undergraduate at the University of Massachusetts, where I had a chance to work with Ding-Ching Lee in the development of this method and model and in GeoTrack the stresses that occur near the onset of these two failures and develop the design charts that we'll talk about in just a few minutes. The design method itself is it handles a trade-off between the ballast thickness required for certain subgrade properties at a site or at a cross section, including trade-offs on track life, number of cycles, and design wheel load. The design considers the allowable subgrade deformation, and here is really a big jump that subgrade deforms. So in good track, we should have a resilient subgrade that doesn't deform, but the reality is in very soft subgrade conditions that sometimes subgrade deformation is inevitable with any load, and that the design method in those particularly soft subgrade conditions requires a specification of an allowable amount of deformation that is chosen by the designer. The subgrade soil type, subgrade and ballast modulus or stiffness, subgrade strength, and other numbers in the chart are the thickness, subgrade thickness, and a design constant of 6 inches for L. So our T over L there gives us thickness increments in 6 inches. The equation for this design method is given here at the top. The other parameters that are in here besides the allowable deformation, the design wheel load, the subgrade strength, number of load cycles are these parameters A, B, and M, which are soil type parameters that describe the behavior of the soil. And there's a factor of A, 1,000 square inches to keep the units in check. And taking that design method and using it in reverse, checking out the track life given in number of load cycles, given ballast thickness and properties, subgrade thickness, design wheel load, we convert that equation into that equation for the number of load cycles shown at the bottom. And to a certain extent, O'Riordan and Fear in this figure show the design life for their track in design life in years for given granular layer thickness, which shows the trade-off in yet another way. You can have if you have a longer design life, you have a thicker ballast layer to protect the subgrade a little bit more, gives you essentially the same type of output. All right, moving on to the risks affecting the track substructure. Maybe not the most problematic, but certainly one of the first ones that'll come to mind is overload. And when I say overload, it is not necessarily the overload from unforeseen circumstances, but changes in applied load. So if the loads changed, if the design wheel load no longer is representative of traffic, or if the applied load exceeds the resistance, then we have problems with in the vertical plane, the tie ballast interface, subgrade deformation, in the lateral plane misalignment and tie and ballast gap when we have a lateral movement in the track, and And longitudinal shown here, the infamous ballast cavity and foul ballast. Environment's another risk. Going to sound like, I guess, run the risk of sounding a little bit like a farmer here, but we have risks related to heat in terms of track buckling, cold in terms of pull aparts, rain in terms of saturation, flooding in terms of washouts and embankment problems, and dry arid conditions with sand and dust blowing into the tracks. So operating a railroad has a risk for every type of condition. I'm going to call out drainage just for a minute, just because when I watched the Hay lecture by Gary Wolf, this really struck a chord. One of his top 12 methods for reducing accidents is improving drainage. Go. Okay, so moving on to the next slide, dynamic pore water pressure. Just one particular outcome of the drainage problem is what happens in track when you have a saturated track support layer. Well, it sort of depends on the state of the soil with the state diagram here, whether it's loose or dense. We can have problems in both conditions. If you have a dense layer that's saturated, you can get this cyclic mobility. If you have a loose layer, we can either get densification or liquefaction. It's saturation is not good, whether it's loose or dense. And the figures on the right are just for those people that are interested in this problem, that are geotechnically focused about the development of the strain, whether it's over a cyclic strain or over a strain over the entire test, shown by the two different figures in the upper right. And what governs that failure, whether it's cyclic strain or total strain, is the shear stress reversal. If we have shear stress reversal, sometimes we get that worse condition where we have failure over a fewer number of load cycles due to cyclic strain. And when does shear stress reversal occur? It occurs under principal stress rotation. So each time a wheel passes, the stress state in the supporting layers changes, and the shear stress reversal shown in column B there reverses each pass. And that's on an incremental basis. We have to make sure that the roadbed is installed in a condition that the static stresses in the roadbed are adequate to overcome these incremental shear stress changes, such that the overall shear stress does not reverse direction. If it does, then you have problems related to dynamic pore water pressure development, since this is a major factor in how fast that develops, and this will certainly affect track life predictions. So what are the changing environments? I think the first one is environmental changes. We're in an era where we have flooding that occurs a little bit more routinely than it did, than we're used to. And I guess maybe what we're used to might not be whatever is, quote, normal. But if we think back to the floods of the 30s and the 50s, at least in my area in the Northeast United States, it's not flooding that hasn't been ever seen before, but it is at a level where it's occurring much more frequently. So severe precipitation presents local risks. The report cover on the right is a report in the state of New York by the Attorney General about trends in extreme rainfall. And if you look at the date, September 2014. So, if you fast forward 7 years and try to write the report now, it certainly would be probably a different punchline than what was foreseen in 2014. But this is a fairly comprehensive report available from the New York State Attorney General website about the effects in New York State. You have to keep in mind that railroads were the first infrastructure after water-based transportation canals. This means that many of the lines were follow rivers and canals, and the railroads that tend not to follow those rivers and canals, even when they branch off, tend to be some of the lowest elevation infrastructure. They were there first. They're the lowest. Elevation is everything when it comes to drainage, and if you're the lowest elevation infrastructure, you're starting out at a disadvantage to get drained. And On top of that, we have our open track structure with the open ballast that lets precipitation in, requiring positive drainage of the roadbed and positive external drainage to carry water away from the track. And the final bullet here, preserving lifelines, these critical infrastructure access to areas inundated with heavy rainfall as shown in the figure, will require improved knowledge of these local factors, local drainage, local runoff analysis, local changes in drainage conditions to ensure proper performance. Operations is certainly another area where things are changing, and in the figure on the right, we see car capacity by year, every year up to 2010. And it was pointed out to me yesterday that I probably could get the data and add the bar for 2020 in there. So that's on my to-do list. I'll send an updated presentation with the 2020 bar in there when I get that done. But what are the factors that are driving the changing operations that affect our roadbed? And that's load, train length, speed, and headway. All of these make important elements in our design. Train length, how many load cycles, how fast are they going, what's the dynamic load, is there a rest period between trains? Rest periods can be important for geotechnical material performance. What's the train makeup? Are the loads distributed equally on cars? Is there heavy loads? Coupler length, axle spacing, in the consideration of number of load cycles. If we have widely spaced axles and large coupler lengths, maybe each wheel is an individual load pulse on the subgrade. If we have short axle spacings and short coupler lengths, maybe we have just 2 axles or 4 axles at a coupler. That's a load cycle on the subgrade. And then precision scheduled railroading, really a driving factor here. Could be that if we're going to try to operate a precision schedule, that having a reliable track and roadbed that meets the criteria of Mr. Chipman in that introductory quote might be one of the solutions to this operational scenario. Effects of these factors, the load and the traffic both affect design life directly. The axle spacing, as I already mentioned, affects load count, and delays associated with unplanned maintenance affects PSR. Maintenance, having some perspective on how our maintenance has changed over the years is critical to understanding how we maintain the track, how we design the track for the future. Historically, large track gangs, as shown in that photo at the top, with section personnel that were very familiar with the local track. Current, we have division mechanized gangs, division personnel that have much more territory, more miles, and certainly good local knowledge, but just fewer numbers to do the personal attention and shovel packing of settling ties and things that maybe was done historically. In the future, we might have some benefit from the Internet of Things, although I have my doubt about the battery life and sensor life of a lot of these sensors relative to track life. We have some track out there that's exceeds the life of most sensors that would be considered an Internet of Things type of device by multiple times. And coupling with that, fourth industrial revolution, railroading 4.0, having better detection, monitoring knowledge of the lifespan of the track and its components would be helpful. But again, going back to the Internet of Things challenges, it presents some issues. And there are other options. Having a sensor isn't the only way to understand the condition. There are remote sensing techniques and other methodologies out there to empower and inform railroading 4.0. So we have two maps here. One of the others is the one of the other considerations is the right of way. How is right of way changed? And I think just for perspective, where I am in Connecticut, if we look at the rail map from 1853 versus 2016, there's a drastic difference in number of lines, drastic reduction, much more rationalized network. And a lot of those lines, even though they're fewer in number, they still retain many of the characteristics when it comes to drainage and subgrade that they had originally. So a lot of continuing benefit from original designs, and perhaps some continuing headaches from things that weren't quite done just right in the beginning. So what's going to be the future of the right of way? It's the 1850s. We had canals, trains, and trolleys. Are we going to zoom from that to the Hyperloop? I don't know. 1950s, we had trains and automobiles and trucks. And 2050, a lot of people are saying it's going to be, driverless auto and Hyperloop. And I'm not sure how that is going to help us as a railroad develop a future. But if we look at trains in the 1850s and 1950s, I have a hard time thinking that trains won't be there in the 2050s. And, maybe our vision for future right-of-way is that ideal track structure, predictable rail freight transit, predictable degradation rates, ideal track. So with that, moving to opportunities to apply the design philosophy to create that ideal track. Number one opportunity is to address risks. These risks include hazards that are natural or environmental related to drainage, erosion, floodplain performance, local geohazards, subgrade, ballast performance, and global geohazards, slope instabilities, and landslides. And the figure on the right shows an image. I got to give a shout out to Dr. Steve Krismer, who helped create this figure in Lee et al. 2015, where we have an ability to apply some knowledge of ballast properties, subgrade properties, to develop a degradation rate to estimate tamping cycles, design life, in other words, which is the heart and soul of the talk and the use of the design method I'm going to talk about today. So common questions we get asked is, how much more damage will some operation have over some other operation, whether it's a maintenance operation or a change in operating conditions or flood, saturating subgrade. How much more damage will be done? And usually when we get into these type of things, the answer comes from some ratio of load increase to the fourth power. And that doesn't really have any local knowledge, doesn't have any specifics about traffic, wheel load, track, maintenance to inform it. So really we have to take a step back and say, if we're going to use this design method, we should really consider how important it is. And, this figure on the right from Willie Everson in 1997 in his dissertation shows the four stages of track life: planning, design, construction, and maintenance, including their time and duration, and their relative cumulative total cost. And planning, design, and construction are just a small part of the total investment that a railroad makes in track. And really during the track life, the maintenance phase is throughout the life of the track, where we have a huge ability to impact that final cost. And applying these design scenarios not only during the design stage to set a design life, but also if we have to go back in for maintenance to set an expectation of the performance of the track after maintenance, would be a big benefit to try to reduce the slope of that cost curve. I had one other figure that I'd like to give a shout out to Jim Heislip for creating for the book Lee et al. 2015. But this figure right here shows, data straight from GPR on subgrade surface, where we're showing a zone of trapped water combined with some surface topography data, and a redesign showing a lateral cross drain, some reinforcement to create positive drainage and stop the saturation-induced settlement potentially at this type of situation. And thinking about that, our roadbed design method provides ballast requirements for subgrade condition based on traffic volume design load. That's great. We can design the ballast thickness. But if we want to convert that to that design into a design life and a degradation forecast that serves as a basis for design validation, we could be asking much better questions about the performance of our track. So if we design that upper track and it starts to form this pocket that traps water, is the track, does it deteriorate faster than design? You know, it's deteriorating. If you don't have the design, if you don't have the degradation forecast, then, you know, it's always deteriorating faster than you'd like, because there's only so much time we have to fix things. But is it deteriorating faster than we thought when we made the design? That's a key question. And then that brings into discussion the possible causes: increased load, inadequate ballast performance, weaker subgrade, environmental conditions, incorrect design approach or constraints. You know, not to leave out the possibility that the design methodology might need to be updated, or the loading might need to be modified. A lot of good questions, better questions, probably better maintenance plan, and easier method to a root cause diagnosis. So, in summary, the ballast design methodology assesses trade-offs among the ballast thickness, design life requirements, traffic volume, and design wheel load. These can be applied during the design phase. These can be applied during the maintenance phase. These can be turned around to predict a design life. These can be used to answer questions about what effect would operating over a saturated subgrade have on my deterioration. If we are going to incur X number of years of deterioration from operating trains for a few months at a deteriorated subgrade condition, then that is a good piece of data to know. Road environment is changing. These trade-offs provide insight to these difficult questions. Some of these questions don't get asked easily. Some of these questions are very hard to answer, and certainly any design method certainly just gives you an estimate of any of the outcomes, but an estimate is at least a starting point to develop better questions that help you evaluate future performance. Risks associated with each of these changes are difficult to evaluate. The risks associated with changes in rainfall, the risks associated with changes in flooding behavior, the risks associated with changes in loading are all difficult. You know, whether it's a local deterioration and mud spot development or something else. But going at it with a design methodology that takes into account the subgrade performance from the perspective of a subgrade squeeze and a ballast pocket helps set performance expectations that one failure mode might be more predominant than another, and that the overall deterioration over a period of time could be expected at a certain rate. And if it's faster than that or slower than that, then maybe we need to modify the design method. I'll finally say that a lot of data is required for these design methods, and we'll talk a little bit about that later today, but the existence of deterioration data on railroad track for given segments is an important element in this design methodology, where the design methodology can be used to back calculate some of the more difficult to obtain parameters. That is a good starting point for some of these, but nothing replaces doing a good site investigation and determining the engineering properties directly. And with that, I think I'm wrapping it up. I thank you for your time, and I know that we have questions, so I'm going to start my video and take a look.
Thank you very much, Ted. That was tremendous. So I also have the questions pane pulled up here. Maybe
Hey.
One question. I don't know if you can see the question that relates to the thickness of ballast when using under sleeper pads. I guess I would throw that question at you first and ask you how some of these traditional track substructure design methodologies can handle kind of the inclusion of elastomeric layers and then how we need to be thinking of ballast mats, under tie pads, et cetera?
So my initial response to the ballast mat effect on the design, I think the ballast mat just addresses some of those early failure problems that we have at the high stress interface between the concrete tie and the ballast, and maybe isn't really associated with the long-term behavior. So one of the big problems we have with concrete tie track is how we build track. And by assembling the track and dumping ballast on it and lifting the track through it and operating trains, we develop ballast chains that tend to concentrate loads on particular corners or edges or positions on the tie that causes deterioration. That deterioration can propagate along or across or expand or go deeper. And those types of problems are mitigated very well, I think, with the ballast mat application. Now, does that change the stress state enough to affect the stress on the subgrade? That's a really good question. If it does, that could affect the design methodology, and it would just require a modification to the design charts to accommodate that. So it certainly could accommodate that, and certainly for the allowable plastic strain methodology that on the ballast, that design chart is certainly adaptable to that modification. But conservation of load in this particular problem, same load in, same load out, I have to think that load goes somewhere, and I'm not sure how that it probably dampens out the dynamic loads, but they don't propagate always down into the subgrade. So it's a good question, but
Yeah.
I think it's really about those premature failures that happen due to that shorten the tie life below sort of the design life because of these problems with how they perform initially, not how they perform long term.
Good response. Thanks, Ted. How about the next question? We focus on the one related to high-speed trains and their effect on the ballast. So maybe talking broadly about specifics of design for high-speed rail infrastructure, and specifically, we see that Christian here, he asked, is there a threshold for operating speeds over ballasted track? And does that have anything to do with the ballasted track itself, or are there other characteristics that limit it?
Yeah, I would say that that's a good question too. Higher, in terms of the U.S. higher speed, which is not high speed, that no, I don't think there's any effects on ballasted track. And in fact, this has been a subject of some research. And at least in North America, even at high speeds, typically the effects on the ballast itself are minimal. The high-speed train effects are really the propagation of the shear wave in the subgrade over really soft subgrades, where we can have an excessive deflection as the speed approaches a resonant frequency with the subgrade, and often on high-speed trains, the roadbed is sufficiently stiff and thick that the subgrade is adequately protected in those situations. But certainly there's a limit. Is there a maximum speed? I'm sure there is. I only wish that we were approaching it and we had that problem.
Thanks, Ted. How about Christian asked a question here saying, is there data on ballast performance kind of over time as we have improved construction techniques and methods? And I've got a follow-on to that, but I'll hold my question.
Right. So there's a lot of data on ballast performance developed over time. There has been AAR studies and TTCI studies, and Canadian Pacific did a lot of work. And there's if you go back to the Canadian Pacific work, there's publications on what ballast life. They actually developed an equation for ballast life that was pretty simple to apply. They also had their specifications of the LA abrasion test plus 5 times the mill abrasion to ensure adequate performance, really getting both the crushing performance of ballast with the LA abrasion test and the fine abrasion that occurs with small strain, the rubbing type of abrasion from the mill abrasion test to really look at the durability of the product. And if you go back to Merle Clausen's paper, and I think it was 1987, he has a great figure with all the different ballast types and their expected life and their failure mode and everything else. So there's good data. in the age of big data, I don't see that type of insight coming out of our ballast studies, but certainly there are ideas out there that should be brought back now that we have much more big data, because I think we could populate that chart a lot more easily with all our measurements.
It's a great response, actually, and that relates to my follow-on question, which is, with the advent of autonomous track geometry systems and they're being more wide, mainstream these days, plus more frequent GPR operation, have we really been able to go back and take a look at what, instead of looking at specific anecdotes of what went wrong at certain locations and what we could do for remediation, have we been able to look more globally at what we're learning in terms of the behavior of track, on a subdivision or a division level, looking at different subgrades and how it's manifested itself in maintenance cost?
I'm sure people have. I have not. I think that is a great question. I know there's been some work by Loram that Jim Heislip was involved with Hamed Kashani about developing a sort of a ballast life model that took into account maintenance and a variety of other things. So there is some efforts there, but from the railroad perspective, on a division and a maintenance cost perspective, I'm not aware of it, but that is an area that's ripe for research. And I think the data to populate that study, much like the ballast life study, is becoming more and more available. It's not a one-off scenario where we go out and measure these things. Now we're having better data on a more routine basis to help inform those questions.
Agreed. We have a question here that asks you to go back to one of the last couple of slides of your presentation that shows a plot of geometry as a function of repeat tamping cycles. Do you mind going back to that? It's asked by Stasha.
Stasha.
Yeah. Elaborating on the slide, one of the last few showing the deterioration of track geometry with repeated tamping. I think they were
that's
a little more detail on that slide, maybe walking through it again. And specifically,
this one I think is probably what he's talking about. This is a hypothetical. So this is one of the towards the end of my time at UMass, we had put together a series of spreadsheets that used the ballast settlement model and the subgrade deformation model, which essentially is the design method used in reverse to get the deterioration trend, and added the settlements from these two models together to come up with this deterioration model that's sort of theorized here. So this is not a set of real data. This is a hypothetical about what could be done in this area. There are these types of models out there, these types of interfaces, but to my understanding, this data is showing a possibility, not an output.
Thanks, Ted. We have a couple of questions that relate to using the methodology kind of in a more extreme environments. I think I saw a question earlier about permafrost locations, and I see a question here from Mohammed related to PD subgrades. Can you comment on the use of the methodology you presented in kind of unique applications such as those?
So permafrost, that question is that's sort of beyond where I feel comfortable with my experience commenting on. That's the closest I've come to permafrost has been in southern Alaska, and that was really cold. But in those locations, the permafrost was not permanent anymore. So that was part of the problem. So it's that's a tough one. So if you want to design ballast for permafrost, again, it's evaluating the stability of the permafrost. It comes down to those basics: how stiff, how strong, and then limiting those parameters. But you have specific failure modes in permafrost that you should consider. So I defer on the rest of that answer to somebody else that knows more about permafrost. On the PD subgrade, I think I saw a question down here. It's PD. That's part of the problem of being the old infrastructure, right? The PD subgrades that we learned with the advent of geotechnical engineering and soil mechanics and compaction technology in the 50s, 60s, and 70s is that these organic materials aren't the best to build on. So we probably should excavate and remove. And, in the 1850s, 100 years before that, building over them seemed like a possibility, and a lot of really unique methods to deal with PD subgrades has been developed, whether it's the corduroy that was used in Canada, where they used removed trees to support the track over these really soft subgrades. But it's very difficult. And I had one experience with a PD subgrade below an embankment that we stabilized with a grouting, just basically trying to confinement, making a grout curtain on either side, and then trying to reinforce it. But that's really unique, and I think just seek specialist help. There's that goes beyond. We're talking about inorganic subgrades when we talk about the subgrade design method that I presented today. So this really gets beyond. When you get into the organics, then it's needs some local help.
Great response. I've got another question here that arrived via different communication media, but given the question is this, given we've already built a lot of our lines, how often do we actually have the opportunity to impact the effectiveness of the subgrade? It oftentimes, thinking about your force chain analogy and some of these established, force transfer paths, it appears that we're dealing with a lot of challenges today, bathtub effects that would be easier to avoid if we had a clean slate start. But what do you think are the cost-effective ways to increase stiffness of the track, increase its performance?
So there's a lot of new technology for ground improvement and subgrade reinforcement that's out there. So there's many options. I'm not going to say that any of them are easy, or it's always better to start with a clean slate and have a sort of a greenfield type of construction where we clear the land, establish the subgrade, build our embankment, and build our track. That obviously is the best. But we're lucky to have the existing right of way. It's an operational system that many would envy. So I don't see it as a hindrance, but a help. And it is what it is. I mean, we have to deal with it. Yes, the track has been overloaded and the subgrade wasn't designed right, and there are options to reinforce it. But again, it comes down to site specific. Seek specialist help. When you have the bathtub effects, it's more of that figure that I showed that had the surface profiling data and the GPR data. Find the depth of the ballast pocket. I'm going to scroll right up here until we find it. That little figure from Jim Heislip. This is a great figure. If I can, hopefully I don't go past it. I went past it. I'm trying to go slow now. Well, sorry about that. I'm going to locate it in the application here and put it up in just a second. But mapping, whether it's LiDAR or whatever, getting the surface profile and identifying the ditch invert, and then designing the drainage to intercept that ditch and invert and drain the ballast pockets. That whole system. There's nice data sets that inform that and help too. Can you see my screen again, Riley? Now that I reshared.
We can, Ted. Thank you.
So this type of pocket, or maybe something even worse, understanding the topography from something like a fly map, understanding the interface from GPR, and then coming in here and reinforcing and providing the drainage and everything. There's good solutions to this, but it's hard to picture an out-of-face operation that would let you do a lot of miles of that on a quick basis. So I guess that's probably the heart of the question. I have no easy answers for that one. I know there's good methodologies that get applied over long distances pretty quickly, but it comes down to addressing these site-specific issues, because geology is local, right? If there's a weak area that shows up under a track, whether it's a peat location or not, it's probably an anomaly and not a systematic problem that affects the entire geology that you just have to address there. So at least that's how I like to think about it. We have many track miles that perform well. It's not like all the track miles have substructure problems. Probably less than 10% of them have substructure problems, but the ones that do need specialist attention that are site-specific answers and solutions.
That's a helpful response. The question that has risen to the top of the list is one that relates to ballast height. Is there a downside to the excessive height of ballast? For instance, if you had over 3 feet of it, Is there a downside in terms of maintenance?
Well, 3 feet of ballast is a lot. If it's certainly, I can't see 3 feet of ballast without some fine material, whether it's fouling or otherwise, to hold it up. But yeah, there's a downside of excessive ballast. If you have too much ballast, too much of a good thing, there needs to be a certain amount of confinement, a certain amount of force to consolidate the ballast and wedge the particles together. And if you get 3 feet from the tie, you're not going to get that consolidation if you place 3 feet of new ballast. So that's sort of the role of sub ballast. So if it's an old roadbed that's developed over the years, like the old Pennsylvania Railroad roadbed that Amtrak operates some track over, or most of its track over, yeah, 3 feet of ballast can be a good thing, because they have some of those old roadbed materials where they really took to heart some of those lessons from the Paul Chipman paper and stiffening up the support of the rail, and they really did a great job with some of those really old ballast layers that are so stiff, and it's hard to picture how they were made. But if it's just loose ballast that's placed new, yeah, 3 feet is probably not the right answer.
Thanks. Maybe let's take 2 more questions. There's one related to, it's an interesting question. I know we don't like organic material in the ballast, but the specific question relates to, do we know anything about specific species of weeds that speed up ballast deterioration? Do we know that level of detail, Ted?
No, I can't say that there's a specific weed that I think, if you have weeds that are growing out of a ballast layer, I think it's a sign you have moisture, and that speeds up deterioration. So I think any signs of growth from a roadbed that's supposed to be well drained is not good. So you often see this if you're on a downslope and you have a cut to fill transition, where sometimes the drainage doesn't flow just right. You can have a backup in the drainage, and sometimes especially in arid climates, it stands out as areas of weed growth because of the water that's there. I've seen that in Colorado and New Mexico. But is there a particular type? I couldn't. My knowledge of weed types is pretty limited. But when I see green growing out of the ballast, it's usually not a good sign for drainage conditions, and that's where I think the problems mainly lie.
And how about as a last question? This is a good fundamentals of railway engineering question. How does the ballast shoulder width play a role in increased load resistance?
So the ballast shoulder width is pretty critical. Everybody knows the ballast shoulder width is an important element of lateral track resistance, because it contributes to lateral stability and track lateral resistance. But in the vertical plane, ballast is a granular material, open graded, and like a pile of marbles, only as strong as how much confining pressure is provided. Not that we would ever build a track on marbles, but if you try to make a stack of marbles and stand on it, you're not going to have very much luck. If you put it in a jar or give it a little bit of confinement, then you're as strong as the marbles are, and you can stand on it. So in much the same way, ballast is similar, that the confinement that the shoulder provides, just a couple of psi from having a proper shoulder that's 8, 10, 12 inches thick, that confines that shoulder ballast. The vertical load tends to create a spreading component as it gets deeper in the ballast, and that ballast is going to try to move out and spread laterally. And if you have that confinement that both stabilizes the ballast and holds it in and counters that action, the roadbed will be more stable. When the shoulder gets too narrow, that confinement is reduced and vertical settlement can develop.
Thanks so much for your seminar today. Good questions on here, and we sincerely appreciate your time and you being willing to give this seminar. But a lot of attendees. Before we wrap up for today, I want to announce our next scheduled HAY seminar. We could have one before then, but we know with certainty on October 8th, we'll have Dave Davis, retired from TTCI, and Steve Wilk of TTCI. They'll be presenting on track design for heavy haul railroads, a retrospective look at the North American experience. So we look forward to having everyone back on October the 8th. And if we have another seminar in the interim, we'll make sure that it is publicized via email. But Ted, thanks again. Have a tremendous weekend, and it was great to spend time with you.
Thank you for the opportunity. I appreciate it.
All right. Bye, everyone. Take care.